My name is Derek Mulholland, and my project is the effect of various modifications to a dye-sensitized solar cell on the power output and efficiency. Currently, most of the world's energy is a result of the burning of fossil fuels. This is not only dangerous to the environment, but it is also unreliable, as there are finite amounts of fossil fuels on Earth. Solar energy has been a promising alternative to traditional energy production. Dye-sensitized solar cells are a possible solution to this global energy issue. Dye-sensitized solar cells are a low-cost, easy-to-construct alternative to traditional silicon solar cells. DSSCs use cheaper materials that allow for the cost of construction to be lowered. Dye-sensitized solar cells use titanium dioxide particles as a semiconductor layer, shown in purple. Photo-absorbent dye is bonded to these particles, represented by the blue dots. This layer is between two transparent fluorine-doped tin oxide glass layers, the top serving as the anode and the bottom serving as the cathode. The cathode layer has graphite on its surface. The FTO plates are held together by binder clips. When light hits the cell, it is absorbed by the dye used in the DSSC. Photons excite the titanium dioxide particles and cause them to release electrons. The orange shading represents the excitation of the titanium dioxide nanoparticles. These electrons exit the cell through the anode, travel through a load, and return to the cell through the cathode. At the anode, iodide electrolyte in the cell is oxidized to form triiodide and is then reduced at the cathode to form iodide again. This redox couple replenishes the electrons and allows for a continuation of the circuit. Figure 5 shows the chemical structures for chlorophyll, and Figure 6 shows the main structure of anthocyanin pigments. These two chemicals are known substances that have the ability to be used in dye-sensitized solar cells as the light-absorbing dye. Figures 7 and 8 show the absorption spectrums for both chlorophyll and the main anthocyanin pigments. Chlorophyll has absorption peaks at about 425 and 670 nanometers. Anthocyanin pigments have absorption peak at about 500 nanometers. Chlorophyll is a known efficient dye because it can capture blue photons, which are the higher energy photons. However, using multiple dyes with different absorption spectra would result in a dye that is able to absorb a greater range of colored photons. Kim et al. Studied how graphene affects a dye-sensitized solar cell. Graphene was used because of its fast electron transfer. This is due to graphene's high charge carrier mobility and high conductance because of its low band gap, which enables the fast transfer of electrons. Figure 9 shows how the dye-sensitized solar cell was improved by using graphene, as the experimental groups have higher voltages than the sole DSSC. Alhamid et al. Evaluated various anthocyanin dyes in their experiment. First, they looked at the concentration of anthocyanins within several organic substances. Anthocyanins are the photoabsorbent material found in some fruits. It was found that choki berries had the highest concentration of anthocyanins, shown by Figure 11. This experiment also looked at the absorption spectra of various anthocyanin dyes extracted from different sources. Figure 12 shows that by combining chlorophyll, raspberries, and hibiscus extract, the scientists were able to expand the absorption spectrum. This principle can be applied to other organic dyes as well. Finally, Chen et al. Assessed the absorption spectrum of various dyes commonly used in dye-sensitized solar cells. The individual absorption spectra for the individual dyes is shown in Figure 13. Figure 14 represents the combined dye that was created for this experiment, and it is clearly shown to have a greater absorption spectrum than each of the individual dyes. The purpose of this experiment is to create the most efficient dye-sensitized solar cell possible by using optimal substances for each part of the DSSC. The alternate hypothesis for this experiment is that a dye-sensitized solar cell with a combined dye of blackberry, chokeberry, and spinach, using graphene as the photocatalyst, a combination of zinc oxide and titanium dioxide as the semiconductor, and indium-doped tin oxide glass plates will produce the highest power and efficiency. The methodology for this experiment is as follows. First, the dye-sensitized solar cell is constructed. This is done by using the glass plate intended for that phase, with a specific semiconductor bonded to one of the plates to serve as the anode. The opposite glass plate is coated with the photocatalyst that is used in that phase. The semiconductor plate is dyed overnight using its respective dye. The two glass plates are held together by binder clips and iodide electrolyte is pipetted into the cell. Phase 1 of this experiment is dye testing. 3 dyes will be used for this experiment. The dyes for blackberry and chokeberries are extracted by crushing the fruits with a mortar and pestle using distilled water, then filtering the solid matter out of the mixture. The chlorophyll dye extracted from spinach will be extracted by grinding the leaves thoroughly with a mortar and pestle, then combining the remnants with 10 milliliters of ethanol. The solid matter is filtered out of the mixture with filter paper. Blackberry dye is used as the control for this experiment. Experimental groups for this phase include each individual dye, then a combination of blackberry and spinach dye, chokeberry and spinach dye, and a mixture of all 3 dyes. Each mixture will be done in a 1-to-1 ratio. Phase 2 is the optimization of the glass layer for the DSSC. This phase will be comparing fluorine-doped tin oxide to indium-doped tin oxide glass plates. The best dye from the previous phase will be used for all cells in this phase and the following phases. The best glass plate will be used for the following phases as well. Phase 3 of this experiment is the use of graphene in the dye-sensitized solar cell as opposed to graphite. Graphene is made by adding 10 milliliters of distilled water and 10 milliliters of heptane into a 25 milliliter beaker. Graphite powder is placed inside the beaker, then inside the ultrasonicator for 3 minutes. Graphene is then coated onto the conductive side of the glass plate used. The best photocatalyst from this phase will be used for the following phases as well. The final phase of this experiment is testing the semiconductor. The variables for this experiment are titanium dioxide alone, zinc oxide alone, then a combination of titanium dioxide and zinc oxide. The combination of semiconductors will be achieved by first annealing the titanium dioxide to the glass plate, then annealing it again, but with zinc oxide instead. The setup for this experiment will be a 100-watt bulb placed 30 centimeters away from the cell, which will be tested for 5 minutes. Voltage, amperage, and resistance will all be calculated using a multimeter. Descriptive statistics will be run using IBM SPSS version 24. A one-way ANOVA test followed by a post hoc Chaffee with a p-value of less than 0.05 will be run. Power and efficiency graphs will be created in Microsoft Excel. Here's my budget, and here's my bibliography. Thanks for watching. Please like and subscribe for more content.